Automatically recording, very nice. How's everyone doing? Sorry for the mix-up. I did not realize. I could have sworn that I still had meetings for the rest of the semester, but apparently I did not. Zoom is very strange. Like it only lets you schedule like 50 meetings, recurring meetings at a time or something like that, and then I thought I'd taken care of it, but apparently I had not. So my apologies. How's everyone doing today? Might wait a sec for people to filter in here. Also, let me make sure these will record automatically. Record automatically in the cloud. Cool. All right. That's better. Okay. Okay, we got 20 people. Okay, so not as much of a meltdown as I thought it would be. I'm doing good, Nate. I'm doing good. Alrighty. Something real quick and then guess we'll get started. Da, 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 da. Oh. 22 people. Yeah, okay. Most people are here. Okay. Yep. Nice. All right. Alrighty. So, sorry for the confusion, those of you just joining. I guess I forgot at the beginning of the semester that Zoom only lets you schedule like 50 meetings, or I forget, it's a certain number of meetings at a time, and it's not quite enough to make it to the end of the semester. And I could have sworn last time I was in the Zoom tab that there were other lecture meetings, but I guess not. But I have taken care of that, so that should not be a problem for the rest of the semester. Okay. All right, so we're going to finish up looking at surface integrals, scalar surface integrals. And then we will start looking at integrals, surface integrals of vector fields. Okay. All right, so just a reminder. So if we parameterize a surface S, let me instead say, well, no, let's just say, if we want to evaluate the integral over a surface S of a scalar function with respect to surface area, we need to first parameterize S If it's not already parameterized, usually it's not going to be. So we give it a parameterization, g of uv. Ooh, sorry. We almost never actually call it u and v, of course. But those are just stand-ins for the variables. And we also have to specify where u and v live in the UV plane, either giving specific bounds for u and v separately, or giving a region where u and v live and then finding bounds later. So first we need to parameterize our surface. Then ds becomes a magnitude of gu cross gv. Oops. dA. And dA is either du dv or dv du, depending on the region D where u and v live. So I just leave it as dA because it could be either or. And then sometimes you might want to switch to like polar or something later, but we might see something like that next week, but not today probably. Okay, so ds becomes magnitude gu cross gvdA. And then we go to the function, replace x, y, and z with their parameterizations. So in the function, we replace x, y, and z with the parameterizations. ds becomes magnitude gu cross gvdA. And then we integrate over d. So the whole thing together is the integral over d of f of guv. That just means replace x, y, and z with the parameterizations. And then ds, capital S, becomes magnitude gu cross gv dA. And that's how we do scalar surface integrals. So the process is exactly the same as with line integrals. I want to emphasize that. So it's like as little that you have to keep in your mind at a time. So it takes up as little space as possible in your brain. It's the same process, except d capital S is magnitude gu cross gv. You're still parameterizing the thing you're integrating over. You're still replacing x, y, and z with the parameterizations. It's just now d capital S is magnitude gu cross gv dA. It is, yeah, so I will, yeah, I'll tell you that again. I'll go over that in a second. Thomas. Yeah, I'll do an example, and we're going to have another thing that you should memorize, and then I'll just mention that after that. Yeah. Okay. But remind me if I forget. Okay, so we integrated over a sphere and also over a cone. And we used cylindrical and spherical coordinates to parameterize those. Now let's look at how to integrate over the graph of a function. So let's evaluate the integral over the surface S of the function z minus x with respect to surface area. Lovely. Where S is the graph of you know, let me just say it. Let me say it this way. Let me say it this way. S is a surface. Z equals x plus y squared, where x goes from 0 to y goes from 0 to 1. Okay, so so this is, since we have z by itself, we have z equals a function of x and y. This is the graph of that function of x and y. So if you get z by itself in terms of x and y, the easy way to do this is just let x be x, y be y, and then z is x plus y squared. So our g of x, y, just to write it out, you may not need to do this, but I like to do this just to not get lost. So x is x, y is y, z is x plus y squared, and we're given specifically x lies between 0 and y lies between 0 and 1. I am not going to attempt to draw this. Luckily, really, there's no need to because it gives us the bounds already for x and y. So we don't need to use a drawing to help us figure that out because it's already given to us. Okay, so that's our parameterization. That's our step 1. So step 2, our ds is going to be our magnitude gx cross gy dA. And here's a shortcut for graphs of functions. Honestly, it's not that bad to actually calculate it, unlike the spherical one. This one is relatively quick to calculate, but it still saves some time, and it's nice to remember, to memorize this. So it is the square root. So let's say this is if you have z is equal to g of xy. So the graph of g of xy. So you get z by itself. The function of x and y is your g. So then you get square root of 1 plus the partial of g with respect to x squared plus the partial of g with respect to y squared. Square root of that. And that works for the graph of any function, g of xy. So in our case, our g of xy is x plus y squared. So our d capital S is the square root of 1 plus, what is g sub x? Sorry, little, okay, maybe it's confusing because we have capital G and little g. Okay, maybe that is slightly confusing here. That's unfortunate, but yeah, it's 1. So this is our little g, right? So 1 plus 1 squared plus little g sub y is 2y. So that squared is 4y squared. And so we just get square root 2 plus 4y squared dA. And I'll write this down later. That shortcut, because it's good to have memorized. And then we replace x, y, and z with the parameterizations. So the integrand z minus x, when we replace with parameterizations, becomes, so z we said is x plus y squared. Minus x. So we just get y squared. Yes. Okay. So let's put this together. Make sure I'm not going crazy here. Ah, okay. Yes. No, we're good. Okay, that's fine. Okay. So we get so we're given that x goes from 0 to y, so x is bounded by functions. So x needs to be integrated first. And y goes from 0 to 1. Our integrand we said was y squared. And then our ds became square root 2 plus 4y squared. And then our dA is dx dy, because we're integrating with respect to x first. So super quickly. Okay, integrating with respect to x, well, x doesn't show up, everything's a constant. So it's just x times all of this from 0 to y. That's just multiplied by y. So we get y cubed square root 2 plus 4y squared dy. And we saw something like this on the homework. Hint, hint, if you haven't done it. We're going to use sub, but it's not a straightforward use sub. We're going to have to do another substitution. So we're going to let u be the 2 plus 4y squared. Then our du is going to be 8y dy. Or in other words, our y dy, which we sort of have here. We have y cubed, but y dy is going to be 1/8 du. So what I'm going to do is I'm going to let y cubed square root 2 plus 4y squared dy. I'm going to let that be y squared times square root 2 plus 4y squared So I'm going to pull out that y dy. Because we know what that is in terms of u. We know what the square root 2 plus 4y squared is. So that's square root u. And then this y dy we said is 1/8 du. We're left with a y squared. So we can actually rewrite y squared in terms of u, right? So u is 2 plus 4y squared. We can get y squared by itself by subtracting 2 and dividing by 4. So 2 plus 4y squared, if we subtract 2 from it, and then divide the result by 4, notice we get y squared, right? So we get rid of the 2, we divide by 4, we have y squared. So that's u minus 2 over 4, or in other words, u over 4 minus 1/2 is our y squared. So now we've written everything in terms of u. When I do u sub, I don't like to change the bounds. I like to just put them in at the end when I bring them back. So we'll do that. So we get the 1 over 8 from the 1/8 u, 1/8 du times u over 4 minus 1/2 times square root u. I'm just going to write that as u to the 1/2. So I'm going to distribute through. So I get 1/8 times u over 4, so that's u over 32, times u to the 1/2. So u times u to the 1/2 is u to the 3/2. Let me just pull that u over 8 out. That'll make life easier. Sorry, 1 over 8. Or I can pull 1 over 6. Nah, that's fine. I'll make it more confusing than it needs to be. U to the 3/2 over 2 minus u to the 1/2. Sorry, that's over 4. Don't really need to go through this whole thing, though. And then we can evaluate that. That's fine. So we end up getting one over 32 2 over 5, 6 to the 5/2 minus 4/3, 2 to the 3/2. Whoops. Which you can check to see if you get that yourself. Okay, spent longer than I wanted to on that u sub. But the important bit is noticing that this was the graph of a function. And so we can just parameterize it. So it's a surface z equals of g of xy. So we can parameterize it as x is x, y is y, z is the g of xy, the function of x and y. And the nice shortcut for d capital S is square root 1 plus g sub x squared plus g sub y squared. So I don't like decimals. Always give exact answers, I would say, Aiden. Always give exact answers. If you're giving a decimal, like that's almost, if it's something like this, involves radicals, it's going to be an approximation anyways, and it's much harder to grade. Always give exact answers when possible. Yeah. In particular, if you give a decimal approximation, it's not actually the correct answer. It's an approximation. So always give an exact answer. Yeah. Okay. So let me just say, remember these. So if your S is Z is some function of X and Y, parameterize as X is X, Y is Y, Z is whatever the function your graph is whatever the function your surface is the graph of, G of X, Y. And then your ds is going to be the square root 1 plus the partial of g with respect to x squared plus the partial of g with respect to y squared, dA. So that's good to remember. So if you can get z by itself, write it as a function of x and y. Also, this works, as we'll see probably on Monday. This works if you can get like y by itself and written as a function of x and z, or x by itself written as a function of y and z. A similar approach, basically exactly the same approach works. So you don't have to memorize this ds thing. You can calculate it, but that's maybe like an extra minute to do. It's nice to remember that. And if S is a sphere, of radius capital R, centered at the origin, but we're always going to give you that, centered at the origin. So you parameterize using spherical coordinates, but you replace rho with capital R, the radius. Whoops. So you get R, capital R sine phi, cos theta, capital R sine phi sine theta, and whoops, capital R cos phi. And then d capital S, this I would definitely suggest memorizing, because this will save you a lot of time. D capital S is going to be the radius squared sine phi. You know what, let me just say, dA is just going to be d rho d theta. That's a dA, yeah.
D rho or d phi?
Sorry, d phi. I said d rho, but wrote d phi. But yeah, it's d rho should not show up anywhere. Yeah, sorry. Thank you. So just remember, this is the same as like when we convert to spherical. dV becomes rho squared sine phi, d rho d phi d theta. Now this is the same, but rho is r. So you can think of it like that, right? R squared sine phi. Rho is a constant now, so I guess you can think of d rho as being killed off and not showing up. But yeah, R squared sine phi, d phi d theta. Very good to remember, because that a lot of simplification goes into that. So if you only have room in your brain for one, let that sphere one be the one. Spheres almost always show up, and that takes quite a bit of time to do if you don't have that memorized. But you could save a lot of time by just memorizing these things. Okay. Okie doke. Let's look at the next chapter. 16.5. Surface integrals of vector fields. So I want to emphasize, like, we shouldn't be thinking of all of these like the line integrals, so scalar line integrals, vector line integrals, scalar surface integrals, line or vector field surface integrals. You shouldn't be thinking of these all as like very separate things and you have to remember how to do each one separately. They all, evaluating all of these integrals is basically the same steps that I've outlined every time, except the d whatever thing is going to change. So for, we'll see when we get to it, but for for line integrals, we have for scalar, we have d little s. D little s is going to be your magnitude r prime t dt, where r is your parameterization, and dr is going to be just the vector version of that without the magnitude. That's your r prime t dt. So for your surface integrals, you do the same thing, you parameterize, and then your d capital S becomes your magnitude GU cross GV dA. Or GU cross GV is your normal vector to your surface. And as we'll see, as you can probably guess, when we do surface integrals of vector fields, we're going to have the vector version of that. And that's just the same thing, but without the magnitude. So the vector version of that. But as we'll see, there's a little bit, just like with line integrals, where if we're integrating a scalar function of line integral, we don't have to worry about the orientation of our parameterization, right? It doesn't matter what direction we go along our curve. If you change the orientation, if you're integrating a scalar function, you get the same thing. But if you're integrating a vector field, you have to be mindful of the orientation because if you change the orientation, then the integral changes sign. So the same thing is going to happen here. We have to worry about the orientation of our surface. We'll talk about that in a sec. And that orientation is going to be contained in this guy here. And so in fact, this might be GU cross GV, or it might be GV cross GU. And we'll see how we take care of that. But yeah, everything is the same process, the same few steps. This one little bit has changed, and that's basically it. So you'll save yourself a lot of trouble and a lot of brain space by remembering that. Okay. So let's take a quick look at what these surface integrals of vector fields are. So suppose we have a vector field. F So you can think of F as being like a describing the velocity at each point of, say, a fluid, right? So think of it like fluid current or like fluid flow, describing the velocity of the fluid at each point. So given a vector field F and a surface capital S, so there's a vector field on R3, we're on R3, we have some surface. So we say the flux of the vector field F across S is just the rate of flow of the fluid, not really of F, but of the fluid across S. But I'll use F as sort of shorthand. So if you think of F as like fluid velocity vector field, at each point it tells you the velocity of fluid. And suppose it can freely flow across S, some surface S. The flux of the vector field F across S is the rate of flow of that fluid across S. So if this is our surface S, and we have a vector field F, so we need to be mindful of what direction the fluid is flowing. So for instance, it makes more sense to describe it with, say, a closed surface. So suppose we have like a sphere. Suppose we have a sphere as our surface. So we could have fluid flowing out, and we can have fluid flowing in. And we want to distinguish between the two. We want those two fluxes to have opposite signs. So what we need to do is we need to give our surface S an orientation. So we give our surfaces an orientation by picking a positive unit normal vector in at each point. In other words, all of our positive unit normal vectors are going to be pointing towards one side. Right, so if you think of a table as your surface, so at each point, there are two unit normal vectors, two vectors which are orthogonal to the tangent plane, although the tangent plane is just the surface itself because it's flat. But you have one pointing directly up of length 1 and one pointing directly down of length 1. So the one pointing up corresponds to the top side, and the one pointing down corresponds to the bottom side. So the way we give it an orientation is we say either the one pointing up is a positive unit normal, or the one pointing down is a positive unit normal. And whenever we give a surface integral, as we'll see, we'll always tell you what the orientation is, what the positive side is. But does that make sense? So you can find the unit, you can find at each point 2 unit normals, right? Remember unit vectors of length 1. So there's always one pointing in one direction, one pointing in the opposite direction. We decide which one of those we're going to call our positive unit normal vector in. Okay. So if we pick a positive unit normal vector, the normal component of our vector field F so the piece of F, the vector field F, pointing in the direction of the positive unit normal of our surface. That's just going to be the vector field F dot the positive unit normal vector in. So we want to know the rate of flow of F in the direction across our surface in the positive direction. So we just take the dot product of F with the unit normal vector in, and that's the piece of the vector field F flowing in the direction of the positive unit normal vector in. So we say the flux of F across S, that's going to be the integral over the surface S of the normal component of the vector field with respect to surface area. Okay, so this is one way you could see this. We'll see it's more commonly written a different way, but let's look at how we would calculate this. So same thing, let's parameterize. Oops. So we parameterize S. With G of UV, U and V lie in D. So in this case, our unit normal vector. So remember we said a normal vector was GU cross GV, a normal vector to our surface. And if we want to turn that into a unit normal vector, we divide by the magnitude. But remember, at each point, we have two choices for unit normal vector. One pointing in one way, one pointing in the opposite direction. So the negative of that guy. So we're going to have to figure out whether it's GU cross GV or the opposite one, which you could say is GV cross GU or minus that. So we'll say it's plus or minus this. We'll have to we need to figure that out. And then we know our D capital S is our magnitude GU cross GV. dA. Wow, that's a D, believe it or not. So putting this all together, this is, so we replace X, Y, and Z in the vector field with their parameterizations. So that's F of G of UV, just replacing X, Y, and Z with the parameterizations. in, we said, becomes GU cross GV over magnitude GU cross GV. It could be GB cross GU. We'll just forget about that for now. So that's our in. And then ds becomes magnitude GU cross GV dA. So now, once again, these cancel. And so let me write it over here. So we get, whoops, so that's the integral over d. We get the integral over d of f of g of uv. So replace x, y, and z with parameterizations, dot gu cross gv dA. Or gv cross gu, or negative of that, depending on the orientation. I'll keep emphasizing that, but you'll get in the habit of it. And that guy, similar to what we did with line integrals, we just say that guy is d vector s. So the gu cross gv dA. Okay, so here's how we evaluate these. I'm just going to rewrite essentially what I just wrote. So if we parameterize our surface S, by g of uv, and we give the bounds for u and v, or say where u and v live. Then to evaluate the integral of a vector field, so f dot in with respect to surface area, which we can also write, we see it more commonly as just f dot d vector s. Those are used kind of interchangeably. We do it the same as we always do. We replace x, y, and z with parameterizations in our function, in our vector field in this case. And then ds becomes gu cross gv dA. And we integrate over d where u and v live. We could get negative of this vector also, depending on orientation. Oops. So the steps are the same as everything we've learned about line integrals and the scalar surface integrals, except now d vector s is our gu cross gv dA instead of magnitude gu cross gv dA. But now we need to be mindful of orientation, so it could be plus or minus gu cross gv. And when we do some examples, I think it'll be more clear. And let me also mention, if you reverse the orientation of your surface, if instead of you have your unit vector pointing in this direction, you have it pointing in the opposite direction. So reversing orientation of your surface changes the sign of the integral. Right? Reversing the orientation means going from GU cross GV to negative GU cross GV. And obviously that's, you can just pull that negative out and that's going to change the sign of the integral. But that is only true for integrals of vector fields. For integrals of scalar functions, orientation is not important. Okay, so we will do some examples of this on Monday, several examples, because that is important. But any questions about this? Okay. If not, have a great weekend. I will see you all on Monday. And remember to turn in those homeworks. And yeah, have a good one, guys. Sure. What's up, Juan?